Okay, hopefully my hand's pretty steady, otherwise you guys are probably getting pretty dizzy by now. Anyway, so we've got section 7.3 about continuous random variables. The major difference between discrete and continuous random variables is how they're, besides the set of values that occur, is how their probability is spread out and how it's described. In the case of discrete random variables, we talk about something called a probability mass function. The idea is if we were to place a piece of mass at the values that have positive probability, you would end up seeing something like what we've got here. It's called a needle diagram. For the unsold newspaper problem, you'll see each needle, the height of each needle corresponds to the, or at least it's supposed to correspond to the probability that were given in that example. I know they're pretty close, but I was trying to do this a little bit by hand. So what we've got there are those individual needles, each having mass corresponding to the probability of that specific value of x. In the case of a continuous random variable, they're described by something called a probability density function instead of a mass function. You'll remember the term density from earlier on in the semester. It relates here too, and the idea is that the density shows how the probability, the total probability of 1 is spread out over the possible values of x. By the way, in case you wonder why I'm not at a table right now, the table where I would do this is right in our dining room, and that's next to where my son is watching a movie right now, and my wife and daughter are in the basement watching a movie, so I'm up here. So anyway, okay, so first off, as far as some examples here, these are just sketches of different types of density curves. The idea is that wherever there is some positive height, here there is probability associated with it. We've got 4 different examples here. In the cases of the upper right and the lower left, both of those continuous random variables have a finite minimum and a finite maximum. In the case of the upper left, the implied minimum is 0, but that curve, the way it's drawn, it's always hard to see this the way it's drawn, but the implication is that that density curve goes out forever, so there is no finite maximum in the upper left case. And in the lower right, as you can see, that is intended to be a normal distribution, and theoretically that goes out infinitely in both directions. Okay, so some basic principles here. The area under the curve, which is total probability, always has to equal 1, just like in the discrete random variables when we added up probabilities we had to get 1. We measure probability here by taking a look at the area under the density curve corresponding to the interval of interest. And one other thing about these pictures is that whenever you have, oops, sorry about that, intervals of the same width, but one interval is in an area where the height is greater than the other, then the area where there's greater height, the region where there's greater height is going to correspond to a higher likelihood. So if you take a look at this picture that's down here at the bottom, I've created 2 intervals. One goes from A to A plus B, one goes from C to C plus B. So they're both the same width. That width is B. But the interval from A to A plus B has the curve is much higher in that case. So the probability associated with x being in that interval is much greater than the probability associated with being in the interval from C to C plus B. Now, there's 3 different types of continuous random variables we're going to talk about. The uniform distribution, the triangular, and the normal. And the normal isn't new to you. We're just going to extend it past what we did before. Okay, so the uniform distribution is defined by its smallest and largest possible values. Those are A and B. This is the density curve that you see right here. One thing to notice with regard to this is that the density curve over the interval from A to B is intended to be a horizontal line. The implication is that if you take an interval of a certain width and you put it anywhere between A and B, it doesn't matter where it is, the probability will be the same. The notion of uniform as an adjective is that. The shape is a rectangle, so the question then becomes, what's the height between A and B? Well, remember that total area is 1, and the area of the rectangle is equal to the length times the height. So as far as the length is concerned, the length of that base is just B minus A. So in order for the area to be 1, that means B minus A times the height has to be 1. So the height is going to be 1 divided by B minus A. Okay. Well, we've got two numeric examples right here. The first one is a uniform 4/8. The implication of that notation is that the minimum is 4 and the maximum is 8. So if you take a look at the curve there, the density curve, the length of that interval is going to be 4 from 8 minus 4. And so since the length is 4, the height is going to be 1/4, the reciprocal of that length. In the second case, we're going from 5 to 15. The length of that interval is 10, and so the height is 1/10 over that entire region. So whenever you're doing probability calculations with these, you're going to be calculating the area of a rectangle. And so it's going to be the length of the appropriate interval you're interested in multiplied by whatever the height is for that uniform curve. Sorry about the wobbling here. Okay, so what we've got here, examples involving probabilities here. In this case, we're looking at the time that a bus arrives, and it says that it can arrive anytime between 8 a.m. and 8:15. And we're going to assume that it's no more likely to arrive at any one instant than any other instant. So that statement right there is basically implying that we're working with a uniform distribution, that it's equally likely over that interval. So how likely is it for the bus to arrive later than 8:05? So what we've done here first is we've drawn the density curve. X is the time of arrival. And this is in, I know I wrote in minutes, but it's really in hours and minutes. I'm sorry about that. So as far as the height of the curve is concerned, the length is 15 minutes, the difference between 8:15 a.m. and 8 o'clock. And so the height is 1 over that quantity, or 1/15. And we're looking for the bus to arrive later than 8:05. So what I've done there is I've drawn a vertical line at 8:05, shaded the region over to 8:15, and that's the area that we want. The length of that interval is 10, and like we said, the height is 1/15, so the probability is going to be 10 times 1/15, or 2/3.